discussed what was that? Yeah, we have discussed till the chills and paddings. Yeah, fine. So in today's session, we'll discuss about miscellaneous casting techniques, and these are the these. Okay, let me zoom out a little bit. So this is handwritten notes. I don't have slides for this. Okay, hope it is visible to you guys. Is it okay? Is it visible? All the wordings and all, is it visible? Okay, fine. So let's continue. So the miscellaneous casting techniques, in the sense like the classification of plastic miscellaneous, in the sense that we have discussed only one casting, that was sand casting. Okay, so from there now we'll be discussing about a little bit of more castings. But why these are called miscellaneous? Because most of the castings that they perform in the foundry are sand castings, and these are all castings which will be used only when there is some special requirement, and uh, some material property has to be achieved, or maybe some high what you say, the efficiency, what you say, the tolerances are required. Then you'll go for this kind of techniques. Anyways, like classification of casting techniques we have already seen, and it is categorized into three techniques, three methods. One is expandable molds, and another is permanent molds, and the another is casting, continuous casting. So in expandable molds, what is expandable molds? In the sense, temporary molds. So molds means what? The cavities. The cavities that we create by using patterns are called cavities, right? The cavities are temporary. In sand molding, let's say you are trying to uh, cast, do the casting with sand mold. Then what you do? You put the pattern. You do all this, the ramming, all these things you'll do, and then you remove the boxes. They remove the pattern properly, and then you keep the assemble the boxes, and then you pour your liquid metal. After pouring liquid metal, you'll destroy the complete mold cavity. You'll destroy complete sand, and you'll take out the casting out of it. So you're destroying the mold cavity. So that's why it's called temporary mold, or these are called temporary molds. Under temporary molds, we have sand casting, shell molding, investment casting, full molding, and CO2 mold. So we will be discussing all these things in detail. And another category is permanent molds. In this case, we are not destroying it. We are not destroying the molds. We are reusing it again and again. So these are made up of metallic molds. In all this case, either sand or some other material is used, but in this case, metals are used. So metals you can't destroy it, right? You can destroy it, but destroying it is very difficult. Okay, so we'll be using these permanent molds in centrifugal casting, die casting, and slush casting. And the last one is continuous casting. It continuous means like you have continuous line of processes that are happening. Somewhere the materials will be put into the furnace, and from furnace it will be brought into the place of foundry, then pouring, then cooling. Everything is continuous process. Okay, so let's discuss all these things with the help of diagrams, and these are all I've written, but anyways, like, let's not go into details of it because we don't have much time here. So the first is sand modeling. We have already discussed this. We have already seen what are the gating elements, riser, all the things we have seen clearly. Okay. Now what we'll do, we'll be discussing from second one, that is shell molding. So shell molding is like this. If you see the diagrams, okay, let me little bit zoom so that picture is very clear. Yeah, the picture should be clear. In shell molding, the box is like this. We have one box, okay, and there are some, there's a cover for it. It's called lid. With the lid is covered by using this electric pins. So you can remove and close it. You can close it and open it. Okay. So what we'll do is that we'll take this lid or plate, then we attach the pattern to this. This is called pattern. This is what we are seeing is pattern here. and this pattern will heat it. Okay, this pattern will heat it. So initial configuration of your shell molding box is like this, and below in the box we'll fill it with this mixture, that is sand with resin binder. Okay, so here we have phenolic resin plus sand, so that is what is called sand with resin binder. Resin binder is phenolic resin. Sand is there and we are adding some extra material, that is phenolic resin, and mixture of this is poured into this box, and there is no contact in between these two. Now what you will do, as you have heated this till certain degree centigrade, maybe some some 100 degrees centigrade, something like that, you'll based on the material that you're putting here, you will heat it. That is called hot pattern. Now you invert the box, that is your second configuration here of this thing. When you are inverting in this, what is happening, the liquid, the phenolic resin and sand, whatever that paste or maybe the liquid is there, that is coming in contact with this hot pattern. Now what happens, as you wait for some time, if you are waiting for some time, the phenolic resin is interacting with this hot pattern and some thickness of shell is being formed. Okay, you see, that is what is the third diagram here. Some thickness of shell is being formed because of that hot pattern, and after some thickness is achieved, okay, then what you'll do, you'll directly invert this box, and whatever this thing is there will be again in this position, but now this shell is left with the pattern. So the shell is removed from the pattern, and these kind of two shells are made, and they are assembled with some kind of glue or maybe some adhesives. Then you make some way here, and then you are pouring liquid metal into the shell, and after some solidification, you are breaking the shell. You are breaking it. You cannot reuse it again. That is the reason why this is coming under the expandable molds category, and the final casting is done. Is it clear? The first one. Any doubt in this? So in a nutshell, what we can say, simply we are putting some material with sand and resin binder in this thing, and then some ejector pins are there to open and close this lid. On the lid we are putting this hot pattern, and then we are inverting. We are waiting for some time, and that's called dwell time, and then the thickness is achieved. After the thickness is achieved, then this kind of shells, this, we need two of this to make a complete shell. So then we are making the shells combined together, and then we are pouring the liquid into this, then we are breaking it, and then we're getting this component. So that is what is your shell molding. And the important point that you have to use is, is that here we are not using any water. Please remember, we are not using any water in this. We are not using any water in this. It's only phenolic resin plus sand. Okay. And see, the pattern material is of cast iron, and we are heating it to 232 to 320 degrees centigrade. No water is used in preparing the sand mixture. That is what's important. And the same thing, dwell time is the time through which you are allowing the phenolic resin and plus sand to get its thickness. So more the dwell time, more the thickness of shell. That is what you have to identify here. And then rest of the things are same. And the applications wise, we are using the shell molding for the case of cylinder head, cylinder blocks and IC engines, rocker arm, valve plates in refrigerators. All these things are the applications of shell molding. And what is the usage of this? Because of this, minimum amount of molding material wastage with good surface finish. Obviously in sand, we are wasting so much of material in the terms of gating elements, right? We have seen that casting yield, volume of the casting divided by volume of the casting plus gating elements, the total volume that you're being poured. But here you are pouring whatever is required. You're not pouring much. You're not pouring more and less. Of course, if some extra material is there, but not much. Okay, there's no wastage. What's there? What the shell modeling is claiming. Okay, and permeability. The problem with this thing is the permeability is less, because shell, you don't have much pores here and there. Because of less pores, what happens? The permeability is less. So one advantage and one disadvantage. If pores are there, if some reaction is happening between the liquid metal and the mold, the shell, some gases might be evolved, and then that gases will be trapped inside the cavity casting, and that will be a defective casting. That's not good. Okay, fine. So let's go to the next one. Next is investment casting. So this is very important, and lots and lots of questions will be asked in examination if they are very much interested. And I have visited two HALs. One HAL in Orissa, Koraput. It's an Indian division there, mostly Indian division. There are two what you say, the workshop, not two workshops, two uh, what can I say, the buildings. Okay, one place we have full of conventional manufacturing and all. Another place we have non-conventional manufacturing along with the testing in Koraput, Orissa. And I have also visited HAL helicopter division here in Bangalore. There also I have seen this investment casting done. There in Koraput also I have seen investment casting that they are performing for turbine blades. Here also in helicopter division I've seen in foundry there is an investment casting they are using again for some blades for the helicopter. So very important. And also I've seen so many people have are asked in interviews also explain what is investment casting. So what is the procedure of investment casting? So this kind of questions will be asked in interview as well. So we have to know this thing in very detail. Let's know that. Okay. So this is also known as lost wax casting. Why it is lost wax? We'll come to that. But let's discuss the process. Then we'll come back to see why it is called lost wax. Okay. First, what we'll do is that we have this kind of mold. This is a mold, and this is made up of some steel or some other material which is metal. And in that mold, this is the shape of the object that you want to manufacture. This is the shape of object that you want to manufacture. And there is an opening here. Through this opening, you will pump or inject the wax. After injecting the wax, you know the properties of wax, it will cool very fast. Once it has cooled, you disassemble this mold box so that you can remove this wax pattern out of it. So now I'm telling this is called wax, which is cooled off, is a pattern, is a replica of object that you want to manufacture. Now this wax pattern, several wax patterns are made through this injector. You're injecting, you're trying to solidify it, and several wax patterns are out. All the wax patterns are assembled into a form of tree with the use of this central runner system. This is called central runner. Okay, this is a sprue and this is a runner, central runner, and this is your individual runner to the each object, each pattern. So this also is wax here. This also is wax, and this also is wax. This also is wax. This also is wax. This also is wax. So you are making a pattern tree with the help of wax. So, but these are the objects that you want to have. These are the objects, or these are the castings that you will be using at the end. And now this whole wax pattern, along with central runner and the sprue and the objects that you want to manufacture, you're trying to dip this. You're not trying. You have to dip. You have to dip. You're dipping this thing into a slurry. Okay, what is a slurry? The slurry is this: ethyl silica plus water. Ethyl silica is for good bonding property. Silica, of course, you know, that is sand. That is for good surface finish. Fine grain you are using, very fine. It's not very, you know, coarser, finer. Plus some water. And remember, you are using water also here. In the previous case, we are not using water. In shell modeling, we haven't used water. Phenolic resin plus sand, that is silica. Here, ethyl silica plus water. Okay. Now we are dipping this complete wax pattern into this slurry. This is what is the slurry coating composition. Okay. And now, sir, what is the first image? While you are explaining, I lost connection of image. So this is your steel, okay, mold, steel mold, or maybe some metallic mold, and this is your cavity. In this cavity, you are injecting the wax, and then once you solidify the wax, and that is called wax pattern, and then you are assembling it here. Is it okay? Is it okay, Ravi? Okay. Now you're dipping this in slurry. As you're dipping this in and waiting for some time, that slurry is attached to this wax and some thickness is being formed. Then you dip it, then you dry it for some time. Dip it, remove it. You won't put it for a long time. You just dip it, wait for some time, and then you take it and you dry it for some time. Again, some thickness will be formed. Again, you dip it. Again, wait for some time. Take it out, wait for some time. then some more thickness is formed. Like that, required amount of thickness is formed. After required amount of thickness is formed, now some thickness is formed, that is in the form of coating on the wax pattern. Now what you do, you heat this in an oven. That shell what is there on the thickness or the coating that has been formed will be hardened, and the wax will be melted out. The wax will be melted out because the melting point of wax is very low. As the wax is melted out, you will remove the wax out of it, and then now what is left? The shell is left. Right? Now, as the shell is left, in the shell you pour the liquid metal that you want, liquid metal of your interest, and then solidify. After that, you cut off this parts that you wanted to use it at the end. And this is central nervous system is your waste, because this goes under the what do you say, the cast gating volume of the gates, and this is the volume of the casting that is very important. So yield might be less here. So this is the procedure. First you have to make. So does the shell have a arrangement for riser? Yeah, this is what is riser. Riser is not there. No riser. No riser. No riser. No riser is there. So there is no riser as of what I have seen. There is no riser. It might be affecting. I think the allowances are put onto this wax pattern itself. What I feel is that the arrangements of, because anyways we are pouring it here, we keep on pouring it until unless it is shrinking, we'll keep on pouring it. For solid shrinkage, I think the allowances are put into the pattern itself, I guess. Yeah, fine. Good question. Fine. So this, now you might know, I'll come back to this lost wax. Why it is called lost wax? We are just using the wax as an intermediate one. We are using wax, and then we are solidifying the wax first, and then again we are melting the wax, and then we are throwing it away. That's why it's called lost wax. And also here the important question that can be asked in examination is, what is the pattern material that is used in investment casting? Mostly it is wax. Wax material is the answer. And we can use this for mass production, because this is your object that you want to manufacture. So you are making a big pattern tree. In one go you are making 1, 2, 3, 4. Like that you can make n some whatever based on your items and based on your equipment size and capacity. You will be able to produce that many items, that many castings. Okay, fine. So this is exactly what they are trying. And here, the important point here is accuracy and surface finish of castings are very good here. A very important point. Accuracy and surface finish is very good. One reason is because you are using fine grain, and this shell that is being formed is having good surface finish on the wall, and because of that, the accuracy and surface finish is very good in this form of on the castings. Okay, fine. And please do remember, this process, what you're trying to pour all these things, is done in vacuum. Please do remember this. We are getting the shell out of it. After getting the shell, you are pouring the liquid in vacuum, so that the atmospheric, here we are not designing any runner, there is no sprue, aspiration effect might be a possibility here. So to avoid that, we are pouring the liquid in vacuum conditions, because if there is no atmosphere, there is no chance of getting somewhere in between this negative pressure that is being created. So you are performing this thing in the vacuum environment. Please do remember that. So there are some points. Wax material, surface finish is good. You're performing this in vacuum environment. These are the important points that you have to take home. Okay, and it is very expensive. Obviously, you are doing with the wax. Then again, you are forming a tree. Then you are dipping, waiting, dipping, waiting. Again heating. Again getting the wax out. Shell is formed. You're pouring, breaking it. All these things are big process, and it is expensive. Okay. And what are the applications of this? The applications of this are gas turbine blades, jet engine parts, medical implants, very important. Dentures, these are surgical elements, and gold are. Even if you see, if you go to a gold shop, and if you see some good designs are made in the gold. If you see some gold chains, maybe some gold items, like for the women especially, There's so many different fascinating designs are formed, and that fascinating designs, that complicated designs, can be easily manufactured by using this investment casting. Okay, please do try to understand that. Fine. So that is what is investment casting, also known as lost wax casting, and I also told you why it is lost wax. Fine. Now this is called full molding. It is also known as cavityless molding. Obviously, I'll come to this cavityless molding. Why it is cavityless molding? First, we'll discuss. In full molding, we have the patterns as plastics. By now, you'll be understanding. Here, we are not forming any cavities. We are directly pouring the liquid metal onto the pattern itself. That is the reason why it is called cavityless molding. We are not creating any cavity. And this pattern is evaporative patterns. You see, evaporative patterns. Evaporative patterns in the sense, plastics, polystyrene foams, PVC, thermocol, all these things are having very light density. Because of the light density, if you are pouring very high temperature material, the pattern will be evaporated because of the heat. Okay. So here what we are trying to do, we are putting the patterns. This is the pattern, and in the pattern itself, we are putting all the gating elements. This is your pouring machine, this is your sprue, this is your runner, and this is your molding cavity, and this is your runner riser. All these things are attached and are made in the form of pattern, and this pattern is made up of this plastic light density materials. Now you are putting this pattern into the molding box, and then you are putting the sand and you are ramming it, and then you are not removing it. That is the important point. You are not removing it. You are not creating any cavity. You are allowing directly liquid metal onto this pattern. Because of that high temperature, this low density material will be evaporated. As this pattern is getting evaporated, it will make a way for the liquid metal to get into this cavity. Once it is getting into this cavity, and you will allow it to freeze, and then you break the sand. That's it. And again, here also again you are breaking the sand. Here in these three things, shell molding, investment casting, and full molding, we are breaking the mold cavities. That is the reason why all these three are coming under expandable molds. Fine. So that is what has been written here. And what are the important applications? Tools and fittings, motor casings, and etc. So all these two are the applications for here. What? The full molding or cavityless molding. And this is an evaporative pattern. Please remember. This might be a question also. Won't indentations form? Why do you feel the indentations are formed? What do you feel indentations are formed? Naveen, you are saying that indentations are formed. Why? What do you feel that indentations? Because we are trying to pour here. Slowly it will come here, and we are forming. This is your sprue. Obviously, we will avoid. The evaporation will happen here, right? Here, right? So, you are saying that evaporative materials will be mixing with the metal casting. That is what your problem is. That is what you are asking. Okay. So they won't mix actually because they are very light density. Even though they're mixing, it won't affect much. It's very light density. They'll evaporate. But I didn't see this till now. But I also have read this, but I haven't seen this performing any industry. I've been to so many manufacturing sectors. I told you, right? Like I've been to HL, two HLs. Yeah, because there is no air. Yeah, the sand is there. This is molding sand as it is, like previous sand molding. Air is there. Air will escape. But there's no worry. Molding sand only. If that is the problem, if that is the thing, then obviously they'll escape. But I thought like sometimes there is a chance of this liquid metal is mixing with this kind of evaporative material. That there is a chance, but it won't affect, I guess. Okay, but I haven't seen. To be frank, I didn't see this thing in real. Okay. Now CO2 molding, and this is what we have to do. Simple, same thing. What we have done in the same what we have done in the sand casting. We'll do the same thing, but 1 minute. We'll be doing the same thing, but the thing is we'll create some passages here. And in molding sand, we'll add one extra component. So what is the what is molding sand comprising of? Anyone? Anyone? What is the composition of molding sand? What are the components that are there in molding sand? Anyone who can say that? I have already discussed that. Molding sand comprises of what? There are 4 components in molding sand. So I'll tell the first one. First we have 70 to 80%. Yes, 70 to 80% of silica. Next Naveen, what is that? Okay, we'll add silica. Then of course we'll add some water. Very good. Then additives and binders. Right? Yes, excellent. Excellent, Praveen and Naveen. Very good. Binders. So in that, what we'll do, we'll add this sodium silicate. That is 2 to 6% in the form of additives. Okay. Sodium silicate. And we'll mix it and then we'll ram it. Everything is same. And we'll create some passages here. And through that passages, what we'll do, we'll allow some CO2 pass. We will allow some CO2 gas to pass through this inlets. And there will be some inlet and there will be some outlet as well. Okay. Now, if you see, as the sodium silicate you are mixing in the sand, the sodium silicate is, reacting with carbon dioxide that you are trying to pass, will be forming sodium carbonate plus silica gel. This silica gel is very important. It is tightening. It is hardening the molding sand, and it is increasing the strength of molding sand. And if you see the figure here, as the time is increasing, the strength of the molding sand is increasing. And after some time, even though you are passing for longer time of gassing, then after reaching the threshold value of the strength, and it is saturated and it is a straight line here. Okay, fine. So this is what is your gassing time. This much time you have to pass through the gas. The strength of the mold is increased. Now again same thing, pour it, and then you wait for some time. It will solidify and remove it. Okay. Why we are doing this thing? Because we are getting better surface finish and dimensional tolerance. Obviously, we have these holes and all these things. Because of that, the gas holes and all these things will not form. But the only problem is collapsibility, because your strength of mold is very hard. The molding strength is very hard. To remove the original metal casting out of that thing, it will be difficult for us because we have to break it. So we have to break it very carefully. Because collapsibility is very bad here in this case of CO2 molding. Okay, fine. Next, this is the end of your what is that? Expandable or temporary molds. Let's enter into permanent molds. In permanent molds, we have centrifugal casting, and then in that we have two centrifugal casting. So I'll just not go into details. I won't discuss all this formulation. I'll just tell you the procedure. That's it. What you'll do here in this case, this is a cylindrical object. I mean, I've taken a section of it. Please do not think these are two plates which are like this. No, this is a cylindrical object. I've taken a section of it, and this cylindrical object is inclined with some theta, and then you are pouring some liquid metal into this, and then it is rotated. It is rotated, and once it is rotated, what happens? Because of the centrifugal force, right? Because of centrifugal force, the liquid metal what you're trying to pour will be forming a thickness at the surface of the cylinder, right? Surface of the internal cylinder, surface in the internal cylinder, right? And why we have given this theta? So that the liquid metal that you're trying to pour should cover this complete working length. If it is completely slant, if you're pouring, it might not cover the complete working length. That is the reason why we give slight inclination here, so that the liquid metal what you're trying to pour will take the full working length. And then once you're rotating, this will be obviously, if you know, the center is the line of axis, and then obviously the material, because of rotation, we have a tendency of the material to move away from the axis, move away from the center. So this kind of thickness is being formed here. You see, this is the thickness. Okay, and what is the use of this? So what kind of object we can manufacture here? By looking at this, can you tell me what kind of an object we can manufacture here? If at all you have cylinder like this, and you are trying to pour some liquid metal and you are running it, obviously pipe, very good example, pipes. Good pipes you can manufacture. Yes, pipes, and that too with good strength. Why? Because you are rotating it. All the material density, good density material will be towards the away from the center, and light density impurities will be towards the center, and towards the center material we can remove by using some boring operation, whatever it is. And also the strength is very high because you are trying to rotate, and the cooling gradient also is very high. Because of that, and tough, mostly hard, microstructure is formed onto the surface of the wall. Okay, so that is what is your true centrifugal. True centrifugal because only because of centrifugal force only this material is taking the shape. The next is nothing but okay, what are the applications? Obviously, hollow cylindrical pipes, gun barrels, large size bushes, hollow propeller shafts. Everything, all things are coming under pipes only here. There are all kind of pipes, or you have some cylindrical shapes with inner diameter and outer diameter. That's it. Okay. Next is semi-centrifugal. Why semi-centrifugal? Here we are using we are trying to pour the liquid metal from through a screw here, and you see here this is your object. We have cut into half, and this half, I mean it's not half exactly, we are trying to spread across. This is your axis of symmetry here. Now this is your axis of symmetry, and here we have, this is the axis of symmetry. Obviously this is kind of a mirror image of this and this. You take any section, one side will be mirror image of other side, obviously. Now with this help of screw you are trying to pour. So here the liquid metal is trying to cover, is coming into the cavity with the help of gravity. Here there is no gravity. We are not centering it with gravity. Of course some theta is given, but that's there. But mostly the liquid metal is entering and taking its shape because of centrifugal force. Here we are trying to pour, and the liquid metal is trying to come down with the help of gravity. Once it has come down, when we are rotating, what happens? Again, because of centrifugal force, the liquid metal will tend to move away from the axis. This is your axis of symmetry. It will try to move away from the axis, and it will try to cover all this, cavity here, right? And this is your mechanism, your motor. Because of this motor, this coupling will rotate. Because of this coupling rotate, the total, this thing will be rotating. Because of if you are pouring some liquid metal, it will come down here with the help of gravity. And after coming at this point, what will happen? Because of centrifugal force, it will try to go away from the center, and it is coming completely covering all the cavity. And once it is covered, then obviously you can easily solidify it. Okay, that is what is semi-centrifugal. Pulleys, because pulleys are axisymmetrical objects, wheels are axisymmetrical objects, spoke wheels are axisymmetrical. So all the axisymmetrical objects which are circular in nature, right, which are circular in the sense like axisymmetrical object. Obviously axisymmetric means there is a sweep. In the sweep patterns we have seen, we have taken 2D object and then we have swept it. So on the top view, if you see, there are some circles. In pulleys we have circles, in wheels we have circles, in spoke wheels we have circles. So for axisymmetrical objects we can use this semi-centrifugal. Why semi-centrifugal? We are using gravity plus centrifugal force here. Okay, so this is the semi-centrifugal. Next is centrifuging. Wow, this is the next level. What is that? This is the top view. Okay, this is not side view, this is the top view. So this is a central runner screw system here. So what you do, you make a part here. This is the part that you want to manufacture. So you have this kind of control screw, and this is your cavity. These are all the cavities. Now this is top view. So from top only you are pouring liquid metal through with the help of gravity, and then it is going inside. Because of rotation, because it will rotate like this, because of its rotation, because of centrifugal force, from away from the axis, the metal will be pushed from away from the axis. Because of away from the axis, the liquid metal will be trying to cover this kind of cavities. And why it is called centrifugal? Centrifuging. So you can say that, sir, this is also semi-centrifugal. Yes, but here we have seen axisymmetrical objects, but this is unsymmetrical objects, non-axisymmetrical objects. This object is not axisymmetric, right? But still you are trying to manufacture this by using centrifugal forces. So that is the reason why this centrifuging is used, and this is used for mass production. Hope you are understanding the differences between true centrifugal, semi-centrifugal, and centrifuging. Is it okay, guys? Okay. So next, and why there are less number of people today? I mean, slowly, drastically, this is coming down. Last day it was 13 people, and again, there are 6 people here. Okay, fine. So the applications of this are the patterns of investment castings are it usually absent. I expected that, but I didn't expect the sudden drastic difference. In the last class, when we had on Monday, we had discussion on Monday. We had 13 people. Suddenly, Tuesday is gone, and today is Wednesday. Within one day, I think half the people are dropped. But anyways, like it doesn't matter who are interested, who are really sensitive, they can attend. Right. So the applications of this are like we can use this kind of system to make wax patterns as well. This complete central system, all these things you can pour wax into this. If you're pouring wax into this, it will form a wax pattern tree, right? And this wax pattern tree you can take and dip into slurry, and then you can use it with the you can form the investment casting. So you can use this centrifuging for making the wax pattern as well. Next is die casting. So we are done with the centrifugal castings. Now that is dry casting. Sorry. Now we are doing the die casting. So in die casting we have two different castings. Those are gravity casting and pressure casting. In gravity die casting, we have this kind of metallic die, right? And please remember these are reusable. We can use this reused, and in the previous case also we haven't destroyed our cavities. We can reuse it again and again. That is the reason why this is coming under the permanent modes. Die casting also permanent. So gravity die casting, what is that? You have a die, that's it, simple. And then you are trying to pour the liquid metal into this, try to solidify it, disassemble this with the help of clamps, and remove the object out. Again clamp it in the shape of this, again pour it, again remove it, again pour it. So the same thing keeps on going. So this is what is gravity, and why it is called gravity die casting? The liquid metal is taking the shape of cavity with the help of gravity. That's it. And why it is called die? Because here this die is permanent die. That's it. Gravity die casting. Next is pressure die casting. In pressure die casting, we have two different pressure die castings, that are hot chamber die casting, and next is cold chamber die casting. So what is that? Hot chamber and cold chamber. First, let's discuss cold chamber, then we'll discuss about hot chamber. So this is again a full, and this is what is your cavity, right? This is what is your cavity, and you have a core here. Why do we want to have a core here? What is the use of core? Anyone? What is the use of this core in the die? This is your cavity, and you are putting core. What is the use of core? We have discussed about this core. Why are we putting a core here, and what is core here? Anyone? Guys, what is core here? Yeah, to have a hollow section. Yeah, to have a hollow section. You're right. Fine. Now we have this piston, and this is a liquid metal here, and then we are putting this here. We are directly pouring it. Okay, we are directly pouring it. But here, what we are doing? We are trying to push the piston, and the liquid metal is going here, and then it is getting pumped into this cavity. It's getting pumped into this cavity, and once it is getting pumped into this cavity, you are closing it. You're closing it, and once you're closing it, and this will be getting solidified, then disassemble this die, remove the part, again assemble it, again push it. So why it is called cold chamber, I'll tell you. So this is the procedure, and once the liquid metal is finished here, then you have a space here. You are trying to bring the liquid metal, and you are pouring from. So liquid metal is in the furnace somewhere else. You are bringing that liquid metal, and then you are trying to pour it here. But in hot chamber, if you see in hot chamber, the liquid metal, this complete system, whatever is there, the system is directly attached to the furnace itself. So why we are attaching this furnace to this? Because if at all you are trying to manufacture or cast some low melting point materials like aluminum, all these things are having low melting points, right? So when you're trying to do these things, what happens? By the time you're trying to bring your liquid metal from somewhere and you're trying to pour, it will get solidified. So you don't want that to happen. So you are making the complete system of die as a part of your furnace, and the furnace is hot. That's the reason why this is called hot chamber. And here we don't have any hot chamber that is attached, hot furnace that is attached to the die casting. That's the reason why it's called cold chamber. Same, both are same. The only thing is that the furnace is attached here. That's it. So that's the reason why this is called hot chamber and that is called cold chamber. And then you are trying to push it. Then again same thing. It will take this thing. It will pump. This metal will be pumped into this, and then you try to close it. And then after some time, this will be getting solidified. This declamp it, remove the part out of it, and then again clamp it. Same thing. Same procedure goes on. Okay. Fine. So what are the items that we are manufacturing with the help of cold chamber die casting? That is carburetors, crankcases, fuel injection, pump parts, toilet fixtures, kitchenwares, pressure cookers. So see, this is one good example. Pressure cooker is made by using this cold chamber die casting. Okay. And then in hot chamber die casting also, I mean, I think right, but complex shapes can be manufactured by using this hot chamber die casting, because we are using one point that you have to take away from here is that in hot chamber die casting, low melting points materials are used. In cold chamber die casting, high melting points, low melting points cannot be used. Low meltings cannot be used here. So here low melting point can be used. That is the important point. Fine. Next is last one is flush casting. This we have seen already, but this is little different from the shell casting. Flush casting is nothing but you have some metallic. There is no diagram for this, obviously. So if you have some metal mold, okay, let me. Right. Let me check. Oh, I think I messed up. 1 minute. Okay. Okay. Yeah, it has come. Yeah. So if you have some kind of cavity like this, okay, what the hell is going on here? Okay, we have some cavity like this here, and then okay, not like this. I'll take this car shape. Very bad writing here in this. Okay. Okay, I'll explain it here. Come on, what happened to this? Okay. I think the system is not responding. Just wait for some time. I'll just stop the recording for a few seconds. Okay, guys, are you here? Hello? Yeah, fine, good. So let's start the new topic, that is machining and machine tool operations. So I want to ask one question. If you ever seen this uh, companies, right? If you see the company names are like machine tools, Hindustan Machine Tools, Heavy Machine Tool, Jyoti Machine Tools, right? So nobody mentions Hindustan Machining, Jyoti Machining, but they say machine tools. Why? What is the difference between a machine tool and a machine? In a difference between a machine tool and machining? Machine, sorry, not machining. My question is, what is the difference, if any, between machine and machining tool? Machine tool. Is there a difference or there is no difference? Both are same. If both are same, okay. Both are not same, why? Guys, are you with me? Any answer that you tool is part in a machine. Machine can be in the sense like forging, cutting. Okay. Okay. So the answer is like this. Let me tell the answer. I don't know how many of your tool. Okay, tool is a part of machine is a right statement, but I'm asking about a machine tool, not a tool. You're telling about a cutting tool. Your Prakar is talking about cutting tool. I'm talking about a machine tool. So, and you know what? There's a difference between cutting tool and a machine tool. Okay. So whatever I am saying, the definition, the maybe the understanding of machine and machine tool is this. This might not be available in textbooks. I don't know whether it's true or not, but as of my understanding, what I say, what I think is that this might not be true also, but mostly it is true. Okay, machine is an equipment that converts a raw material into finished good with the help of some energy. That's okay, but machine tool. Oh, sorry. Machine tool. The definition is this. Machine tool is, sorry, I'm coming back again. I'm telling you the definition. Sorry. Machine tool is an equipment or a machine which converts raw materials into finished goods. That is machine tool. Machine is nothing but a generic machine where it converts some energy to another energy. Like your motorbike is a machine. Your motorbike, your automobile, your laptop, whatever it is a machine. What does your motorbike do? It will you'll use a motorbike for transportation. You'll use your laptop for studying, whatever it is. But a motorbike cannot replicate itself. You can't use a motorbike to make another motorbike. But you can use a machine tool to make a machine tool again. Are you getting the logic here? Yes. So this is the definition what I got from somewhere, but it makes very good understanding between the two. But I'm not sure whether this is a proper differentiation between machine and machine tool. This is what I understood as of now. Yeah. Yes. Okay. Good. Fine. Now let's go dig into that. So these are the this is the syllabus, that is mechanics of machining. All the things we'll be discussing anyways. Fine. So first thing is metal cutting. In metal cutting, in machining and machine tool operations, we have metal cutting is first option, first topic. Here the important thing is a tool, a cutting tool. See, uh, somebody told a tool is a part in a machine, sir. Prakar, I think. Yeah. A cutting tool which is harder compared to workpiece. Let's say if it is a vegetable, you have some potato on your tray and you want to cut it. You'll pick up a knife, that is cutting tool. So here we can take an analogy of workpiece compared, equivalent to the potato in your hand, and cutting tool can be a knife. Obviously, the knife that you're holding should be harder compared to the potato. Like this, in terms of metal cutting, a tool which is harder compared to workpiece is used to cut the workpiece using mechanical forces. Obviously, you're using mechanical forces. And it is a subtractive manufacturing process. You're removing the material and then you're trying to form the shape and size of it. You're trying to shape and size to make the shape, and also you're trying to reduce the size of the workpiece by using this tool, which is obviously harder than the workpiece. And this is conventional metal cutting. In non-conventional, we won't be using mechanical forces, and tool need not be harder than the workpiece. There are so many other things we'll be discussing that in the non-conventional machining process, but this is conventional. So of course you have a machine process. we have okay, we have a machining process, and we have so many inputs: power, raw material, machine, fixture, tools, environment. What is environment? What is environment? Cutting fluid, all these things are environments. Then workforce, obviously workforce. Then using all these thing inputs, you have a machining process. With the process, you will be producing some product, and then again the same thing. This is what I have told you in the first class, right? From earth, material, process, all these things, closed loop. Here also, it's forming a closed loop. Obviously, after analysis, you'll have some feedback, and that feedback in the form of error, the error in the form of feedback will be going into this environment tool. All these things will be taken care of. Fine. Next. Why are we reading this machining? So what is the purpose? Because we are trying to estimate at what velocities we have to move our cutting tools, at what cutting forces we have to uh, uh, use, what are the cutting forces that we have to use. So obviously, if you want to cut potato, you use some different force. If you're cutting carrot, you'll use some different force. If you're cutting apple, you'll be using different force, because each and every fruit and vegetables are having different properties. In the same way, different materials will be having different properties. Because of that, you have to have different cutting forces. So without estimating it, you can't proceed. So you have to estimate the cutting force. You have to estimate the cutting velocities. Thereby, if you see, force into velocity gives you to cutting power. So the cutting power, this much power is required. That cutting power will get it from some motor rotations. That motor rotation will be getting it from what? The electricity. And that so we'll go back and try to analyze which kind of motor we'll be using for rotating something, so that we can generate that kind of a cutting force. And also we'll be able to analyze and understand how much consumption is required. So the power, we are trying to estimate the size of prime mover in the sense the machine, the electric machine, so that high capacity machines are required or low capacity machines are required to cut so things. That's it, right? If you're giving a knife and you tell to what you say, cut some hard vegetable, take any carrot. Let's say if a small kid is there, maybe 1 or 2 years old, if you're giving a small knife and you tell that person, small kid, to cut the carrot, the kid might not be able to cut, because the capacity of this kid is very low, right? So that's what we are estimating, the size of prime mover, is the capacity of the electric motor. Okay, that is the aim. Okay, now in cutting tools, now Prakar, that's what we are coming. The tool what you are saying is this thing, that is cutting tool. The cutting tool, we have two different type of cutting tools. One is single point cutting tool, another is multi-point cutting tool. Single point cutting tool is nothing but you have only one cutting edge. We have only one cutting edge like this. Like knife also is like this, only one cutting edge. This is only one cutting edge. So if at all, if you see, are there any? Okay. If you see, there is a grating. You have this grating system. You see that? Remember, this is a grating system, right? Grating system like this. So these are all multi-point cutting tools, right? You have carrot and you want to grate it. You just move up and down. The carrot grates will be falling on the other side. So these are all multi-points here, multi-point cutting. But knife is a single-point cutting tool. So this vegetable example I am comparing every time because for your clear understanding. Okay. So if you are taking, if you are taking this single-point cutting tool, only one cutting edge is in the action. So examples for that are turning. In turning, you might have seen the simple bar is there, which is being rotated. In that will be, having some kind of a tool, and the single point is in contact with the workpiece, and then you remove the work material. Facing also is having a single point cutting tool. And multi-point cutting tool is nothing but you have more than one cutting point in action, more than one cutting edge in action, like milling, drilling. How many cutting points are there for drilling? Anyone can answer this question? What are the number of cutting points in drilling? Anyone? Hello? No. In drilling, we have two cutting points. 2. Yes, Praveen is right. 2. Yes, Madhusudan also is right. Yes, 2. In grinding we have so many. In milling we have so many. We can't define it. But for drilling we have seen it is 2. I'll show you when we are discussing drilling. I'll show you what are the 2 cutting points. Okay. And this is lathe machine. This is a simple controls for your spindle controls and all these things. And this is your chuck. Chuck can be of 2 types: 3 jaw and 4 jaw. 3 jaw is a simultaneous chuck. Like one jaw is moving means the other 2 jaws also will be moving in the same direction where the first jaw is moving. 4 jaw chucks are independent motions. Like one jaw, 2 jaw, 3 jaw, 4th jaw, all are independent to each other. You can move whatever you want, which jaw in which direction you want. But 3 jaw is simultaneous movement. Like the 3 jaws are linked to each other. They are not independent to each other. Now you put the workpiece into this jaw, and then you have this cross slide. In this cross slide, you'll be putting your tool on the tool post, and then you make the tool post in 2 directions. One is depth of cut. If you're moving this in this direction, this is depth of cut, and if you're moving the tool in that direction, it is called feed. I hope you're understanding the difference between feed and depth of cut. You know that, right? Depth of cut is the plunging action, how much deep you're digging in, and feed is nothing but how much cross slide, tearing. Like if you're stabbing someone, if you want to stab a fruit, let's say if you're stabbing a fruit, okay, I'll tell you what is the difference between, okay, if there is an apple, like this, okay, if there is an apple like this, so you are plunging, and you are moving it, you are cutting it, okay. How can I show that? You're cutting it like this, okay, okay, okay. Plunging is in this direction, and if you're seeing from top view, you are cutting it like this, you're making an arc. You're understanding what I'm saying? I can't show that. Okay, apple is there, you dig it, you push your knife into it, and then you cut it, right? You move in some clockwise or anti-clockwise direction, right? The digging is called depth of cut, and moving in clockwise and anti-clockwise with some speed, and that is called feed. Is it clear? The analogy is clear? Yes. So that is what is depth of cut and feed. As of this, the analogy what I've told is not exactly same, but kind of like that. Okay, fine. And then this tailstock is supporting your workpiece so that it won't bend in other 2 directions because of this depth of cut and feed. And this, you have gearbox, so that if you are having automatic feed, this gearbox will be having some gear reduction and all these things. The feed will be given according to that. And the lead screw and feed rod, all these things are a part of lathe machine. You can just try to search Google and read about something on lathe machine. Not much in detail, but let know something on that. Not much. Next. So let's close the discussion for today, and let's discuss. Okay, one mistake that I have done today is that when my system got stuck, somehow the recorder got stopped. Okay, so the recording is not complete today. Only 1 hour of recording has come. So you people are in advantage. Who want to listen the class, they might be in disadvantage, but no problem. Those are only metal casting defects and miscellaneous casting. So I hope it's not a big issue. But let's see what your Dinesh sir will say. Anyways, this is the end of today's class. If you have any doubts, please let me know. We'll discuss now. If you are okay, then we can leave. Thank you. Any doubt? Guys? Okay. Thank you. Okay. Feed part. Okay. You want to repeat the feed part. Okay. Fine. So if at all, this is your workpiece, and this is your chuck. and this is rotating. Hope you're understanding this. Now the tool will be coming like this. The tool is like this. Okay, and you are going here, and how much depth you're going inside. This is depth of cut. Okay, and now you have to move this side with some speed. Depth of cut will be in mm. You have to move this thing with some speed. Slowly you have to move, and that is mm per revolution. That is what is your speed. In this direction is your speed. Yeah. Yes. Any other doubts? Yeah. Yeah. Fine. Good. Fine. So let's meet tomorrow, and hope I'll ask. Please join as early as possible, because we have to. 10 minutes also is very important, because in 10 minutes we can solve 20 questions, maybe some 15 questions at least. So please don't delay. Try to have your dinner as soon as possible after your 6 to 8 p.m. class. Try to attend, come to the class minimum at minimum at least by 8:35. Okay. Thank you. Thank you.